All right, everybody. We are going to learn today about the laws that Kepler came up with for planetary motion. Very, very important laws that really define how we think about the way that planets and the Earth move inside of the solar system. So I already wrote some stuff down here because I realized that I wasn't recording properly when I started, so you can copy these down. Do a little bit of history here to start. We'll talk about something called the geocentric model. The geocentric model was something that was introduced. It was something that was believed by the ancient Greeks. They always thought that the Earth was at the center of the solar system. But this gentleman, Ptolemy, around 150 AD, came up with a model for it. And it was called the geocentric model. Geo meaning Earth, centric meaning at the center. And the idea was that the Earth was at the center of the solar system. Then there was an astronomer named Nicholas Copernicus who came around and came up with the idea, I believe, around the 1500 mark, so quite a bit of time after this. And the model that he introduced was something called the heliocentric model. And what that model is the model that we still believe and know as fact today, is that the sun is at the center of the solar system and Earth is just one of the planets that orbit around the sun. So that is our heliocentrism, we call it. That's the heliocentric model. Now Kepler followed this model and introduced his own three ideas that we're going to talk about in today's lesson. The three ideas are as follows, and this was about another 100 years later. So the first main finding was that objects move around the sun, like we said, the heliocentric model, but they move around the sun not in perfect circles. They move around the sun in ellipses. So they have elliptical orbits. So if this was the sun right here, they have elliptical orbits with the sun being at one focus of the ellipse. So basically how an ellipse works is if we have a circle, we have an equal distance around that center of the circle the entire time. Makes a perfect circle, and that'll be our perfect circular orbit. An elliptical orbit places a focus, places another focus, like that. So rather than just having one focus for a perfect circle, we have two focuses. And then we have an orbit that goes around the two, and it'll look something like that. Something like that. Okay, so that is our elliptical orbit of planetary motion. This is what he came up with. So if this right here is the sun, there's not actually any object here, but it's just the other focus for our orbit. So this could be the orbital path of Earth. Now we have a couple distances that are important here. We have this distance right here. This is the minimum distance, R min, we call it. And then when it's at its farthest, way over there, we call that R max. And the thing is now we have a radius of orbit that's changing. So in order to be able to find what our average radius is, we call it the mean radius, R mean. We have to do like we normally do for finding the mean of an object. We take the min value, R min, and we add the max radius value, R max, and we divide by 2. So that's our formula there to find the mean radius. Whereas with a circle, the radius will never change. In this scenario, it's changing all the time. So by finding the mean, then we can still use a radius to calculate certain questions that we are trying to use it for. So the second finding that Johannes Kepler had. Johannes Kepler also discovered that a straight line joining the sun and an object's path sweeps out equal areas in equal times. Now, what does this mean? Let's draw out our elliptical orbit here again. Let's draw the sun and our other focus. And let's draw our orbit. Something like that. Let's fix this one up a little bit. Okay, and what this second idea here is stating is that when we get closer to the sun, the gravitational pull of the sun, when we get closer, our object in motion will speed up because of the gravitational pull, and it'll slow down a little bit here. And what ends up happening is that we have, if I sweep out areas, so for example, if I take a spot right here, now this isn't going to be, the drawing's not going to be perfect, but if you just follow along with the math, it will work out. If I take this area right here and this area right here, and I sweep out that full area there, and then I do my measurements to make an equal area all the way over here. So basically what I've done is these are a bit closer together, but it's a longer distance away. And I sweep out the area of this as well. So if I state right here that these both have the same area, if that's the case, then that means that they will have the same time. Delta t, delta t. They're going to have the same time. So as long as the area swept out around by the object around that orbit's path, that elliptical path, as long as the area is the same, the amount of time taken to cover that area will be the same. And this goes for literally any swept out equal area size along this elliptical path. So if I had here, this could be the same size, maybe this is the same size. As long as the area is all the same, then the time will be the same too. Was the second thing that he discovered. Now, the third thing that he discovered was just a relationship. He noticed that if he took the radius of orbit of an object and he cubed it and he divided by the period of that object's orbit, with that object's orbital period being squared. So if you took the radius cubed divided by the period squared, he always got the same answer. Always got the same answer. And that answer that he got was a new constant that he discovered. And we call it the Kepler's constant now for that reason. It's called Kepler's constant. Kepler's constant. And it is equal to 3.35 times 10 to the 18 meters cubed per second squared. That is Kepler's constant. Okay, and we'll put a little square around this. That's an important value. You'll see it on your formula sheets. And this is an important value too. Put a square around this too. This is a formula that we will use a lot in this section. Okay, so it doesn't matter how big or how small the radius is, but if the radius is cubed and the period that it takes, how long it takes for it to complete one revolution is squared, and we take and we divide the one by the other, we will always get Kepler's constant, 3.35 times 10 to the 18. That's what he discovered. So he discovered these three things. We'll talk a little bit more about him and his history. I have a video to show you in class. But it's just another classic case of unaccepted and unappreciated genius in its time. Unfortunately, he is another sad case of a lot of his discoveries and findings only becoming common knowledge and commonly accepted knowledge after his passing, after he had passed away. So a genius, but not appreciated in his time. So let's move on. Let's do an example. A small asteroid orbits the sun every 30 days. How far is it from the sun? So now we know how to do that, which is great because of Kepler. We take this formula here, and we know that the period is in days. So T is equal to 30 days. We're trying to find R. We know K. K is equal to 3.35 times 10 to the 18 meters cubed per second squared. So we write this S, but we notice that our period has to be in seconds. Right now it is in days. So I'll let you just pause the video for a second here if you want to try that conversion on your own. Try to convert 30 days to seconds. And if you've paused and now resumed, you should get 2,592,000 seconds is our period. And we're trying to find R. So I need to multiply by t squared on both sides. My formula that I should get is R squared. Let's use purple here. R, sorry, not squared, R cubed equals K times T squared. So in order to cancel out a cube, we have to take the cube root. So find that on your formula or on your calculators, but we have to take the cube root, cancel those out. So our final formula should be R equals the cube root of K, which is 3.35 times 10 to the 18, multiplied by T squared, which is 2,592,000 squared. All of that, the square root. So just be careful putting these into your calculator because these are now kind of gigantic numbers. So any small mistake will end up being a very drastic difference in your value comparatively to what maybe you're supposed to get. If you make a mistake, if you do plug it in all properly, you should get 2.8 times 10 to the 10 meters should be your final answer. That is the radius of orbit of that small asteroid. So there you go. We are now moving on to calculating some stuff about space and orbital periods and radiuses. So you can try some of those questions on your own. Be sure to make sure that you're taking a look at your formula sheet because there are some pretty important constants and some information on the back side of that formula sheet that you will need. So take a look at that. We will have some time in class to do some of these problems together. So if you're not feeling comfortable with them, just leave it. As long as you've got the notes copied down, you're in good shape, and we will see you in class soon.